It's chapter 16.2. And it's line integrals. Just getting this guy set up. That looks skewed to me. What the heck is my brain saying? Like, does that look at an angle? I mean, I'm so easily distracted. That's going to bug me.
Yeah, it's at an angle.
Right.
There you go.
Is that pretty?
That's better.
Try to get this side in. How about that? Can we live with that? Looks okay? Right. I don't know what's happening to my camera, but I was saying to my other class, I've only got one good eye, and if you've only got one good eye, horizontal looks weird to me. If I think it's horizontal, it's actually about 4 or 5 degrees out. So when it looks good, it probably looks slightly out to you. So go figure. Okay, now I've already got the thing set up. Hopefully I can go and show you an intro to what's called a line integral. And I don't want to draw a picture if I can get away with it. So maybe they've got one I can use so that you know what exactly you're finding. Yeah, okay, this might work. Okay, hesitating. It's my usual thing when I don't know what the heck I'm doing. Okay, here goes. What is a line integral? Here we go. If I don't worry about the details around it, we'll worry about that when we come to how you actually calculate it. But can you imagine that you've got a curve on the floor, right? The XY plane. And that curve is called C. Can you see it along the bottom here? That's, although it's called a line integral, I guess you could probably call it a curve integral, but line will do, right? You start with something on the ground. I want you to then imagine that you've got a function f of xy. So that every given point on that line, can you see that the function would take it to a z value? When you calculate the line integral of the function xy along the curve C, what you're finding is the area of this curved fence. Right? It's along the floor, right? It's a C, and then it goes up different heights. So can you imagine you're building a curved fence? So when you find the line integral, that's kind of what you're finding. I don't know if that helped or just made life even more complicated than it needs to be. But I want to at least try and give you a visual idea of what we're calculating, because it's really going to be pure algebra after this, right? So let me see if I can try my own version then. Imagine you've got a function f of xy equals x squared plus y squared. Another way of writing that would be to say z equals x squared plus y squared. Okay. Now, if I draw that surface in 3D space, just asking for a lot, it looks like that. In fact, you might have seen that. It's quite a common shape, isn't it? Right. Now, Can you imagine on the floor, I need another colour. What colour have I got to play with here? Blue. Can you imagine on the floor that I have a curve called C? And it starts here and it finishes here. Now, if you go along that curve, can you imagine that as you travel up, it touches different pieces of that surface, and what you end up with is a little guy that looks like that fence. The area of that fence is the line integral of f of xy, and they use ds as the notation. And that's the best I can do. If you can visualize that horrible drawing, well done. If not, well, you just accept that a line integral creates a number that represents something that could be of use in a mathematical situation. So, how do you calculate them? Well, we need to do some skill building. In particular, we need to get good at parametric equations of lines and curves. In 2D and in 3D. So I'm not even going to go near a line integral for a while. We're just going to figure out how you can get parametric equations of things. So to remind you of a parametric equation, x equals t squared, y equals 2t plus 1. That is called a parametric equation. Basically, if you had x and y, right, representing the x and y coordinates, for every value of t, don't you generate a point? And if you imagine this as being x and this as being y, at t equals 0, you would get 0, 1, which would be here. At t equals 1, you'd get 1, 3, which is about here. And can you imagine, one of the things about a parametric that makes it different from a usual curve is, isn't there a direction that you travel along the curve from t equals 0 to t equals 1 to t equals 2? So it's much better at modeling movements. So right now, this line curve that we're about to calculate has a start and a finish, right? You start at this dot and you travel to that dot. And we need to know that because when you do limits of integration, don't you need to know what the start and finish number are and how you're going to get them? Right? So let's look at lines in 2D. So suppose I gave you a point 1, 3, and I gave you another point 2, 7. And I wanted to know the equation of the line joining P to Q, right? But I'd like to get that equation in its parametric form. How do we do that, right? For 2D, your formula is going to be this. Oh, come back to that. Let's show you what it looks, oops, I don't know where that came from. What it looks like in just normal world. Can you remember calling these guys x1, y1, x2, y2, and then we get the slope? So it's 7 take away 3 and 2 take away 1, and that's 4 over 1, and that's 4. And then you'd go y take away y1 equals m brackets x take away x1. And then you plug in that guy and that guy here. So y take away 3 is 4 lots of x take away 1. Add 3 to both sides, you get that. Right, that was a very quick Math 94, how to get equation of a line in 2D when you know the coordinates of the 2 points. Are we good on that? Now, we're going to try and make a parametric version of that, right? Something with t's in it, right? That's our goal. So first thing I'm going to introduce you to is a guy called the direction vector. So we have the point 1, 3, and the other point is called 2, 7. And the reason I'm going to do it this way, which looks a bit clunky, is that this method is going to transfer directly into 3D straight lines, and then from there 4, 5, and 20 dimensional lines, right? So it's going to be the same basic method. Now, to get the direction vector, you basically find the rise and the run. So if that's x1, y1, and this is x2, y2, the difference in the x's is 2 take away 1. The difference in the y's is 7 take away 3. And the direction vector is 1, 4. Now, this guy here, I'm going to have to figure letters of the alphabet to use for this. I think they use A and B. Do they use A and B? Who cares? I can make them on letters. Let's call this A, call this B. The initial point is P, so we'll call that guy x1, y1. The parametric equation is x1 plus at and y1 plus bt. So in this question, it's 1 plus 1t, and it's 3 plus 4t. So we get a direction vector, which is basically the difference in the x's and the difference in the y's. That direction vector generates two numbers, a and b. The a goes here and the b goes here. Now, this is, right, if I just write it down separate, this guy represents a parametric equation of the line joining these two. I could check it out. When t equals 0, what coordinate do I get? Well, I get 1 plus 0 and 3 plus 0. Don't I get the point 1, 3? Ah, have you noticed that t equals 0 is the starting point of the line? Now, the only other line I know about is this guy up here, Q, right? This guy here. Now, if I plug in t equals 1, won't x be 1 plus t, which is 2? And won't y be 3 plus 4, 2 is 7? Can you see I get q? Have you noticed by this parametric process, can't you do a line from P to Q, get its parametric equation, and you know what the start and finish t values are? T equals 0 will be the first guy, and t equals 1 will be the other guy. Right. Do you want to see another 2D one before I show you a 3D straight line? Are you cool with what I did to 2D and I can move on? Okay. Then I would like to know the equation of a straight line in a line in 3D. And I'll tell you what the equation is going to be. Well, the points are going to be, how about 1, 2, 3 to 5, 10, -3, right? So I want a parametric equation of a line going from P to Q. The equation is going to be x1 plus at, y1 plus bt, and z1 plus ct, where x1, y1, and z1 will be the coordinates of the first point. And ABC are going to be the components of the direction vector. That's the vector joining P to Q. So the direction vector V is the vector joining P to Q. So 5 take away 1, 10 take away 2, and -3 take away another 3. Are you happy about where that came from? P to Q. This is A, this is B, and this is C. So our equations, I guess I could squeeze them in. X then is going to be 1 plus 40. Y is going to be 2 plus 80. And Z is going to be 3, take away 6t. So for whatever reason you need to, are you comfortable that if I tell you that there's going to be a line going from P to Q in 3D space, that you now know how to get its parametric equation? Do you want me to do another 3D one, or do you feel comfortable about this process?
I think it's fine.
Okay. Have you noticed that the way I did it was a bit clunky for 2, but doesn't the 2D one transfer into the 3D one so smoothly? Not that you're going to see a question, but theoretically, couldn't I also do 2 points in 4-dimensional space, right? P is 1, 2, 3, 7, right? Something like that. Couldn't I expand this to 20-dimensional space? And it would essentially be the same process, just with more letters in the alphabet, more variables. So far, so good? Right, now, that's for straight lines. Let's do curves now in 2D. And they're going to boil into 2 versions. Circles and not circles. I don't know what else to call them. Let's do the not circles first. Suppose you want to get the parametric equation of that curve. That could be an issue, you might think. The good news is it's not. It's almost doing nothing. Would you agree if you make xt, won't y just be t squared plus sine of t? And if it was y equals x cubed, won't you do x equals t and y equals t squared? You could do it the other way around. You know how some curves are written like that? That's because they kind of zig vertically rather than horizontally, right? Well, I can do that. Won't I just make y equals t and x is t squared plus 2t? It's almost a cheat, really, isn't it? But it's parametric and it works. And is this unique? No, it's not. Actually, none of the ones I've done are unique. Do you know how I did the equation of the lines? Do you know if you decided to do a multiple of the direction vector, so instead of using the numbers 1, 2, 3, you decided to use 2, 4, 6? Do you know that would also be a parametric equation of that line, right? So parametric equations are not unique. I'm just telling you how to find the most obvious version of it, right? That's all I'm showing you. I think we're good at this. Are we cool with 2Ds? Right. Good news, you don't need to worry about 3D. If you get a 3D curve, they will tell you the parametric equation because they're too darn hard to create. So they will just tell you x is t squared, y is square root of t, and z is sine t, right? They'll just tell you. So now we need to work on circles. How to do in 2D, right? 2D circles. Well, I'm a kind of visual person, so here it goes. X squared plus y squared equals 4. There are two different approaches to circles, parametric equations for circles. The first one is to realize that you could rewrite this guy like that. Now, if I decided to go this route, we have a few problems. Isn't this plus or minus very unsatisfying? Because it's really two equations. Doesn't it depend if it's the top half or the bottom half of the circle you want? But it is quite useful if you only want the top part, because don't you use that guy? Right. The other one is less obvious but more useful. Can you see that that is the parametric equation of this fella? Now, I'm telling you the answer without, really explaining much, but it's very closely connected to polar. Remember r cos theta and r sine theta? Well, in this case, wouldn't it be 2 cos theta and 2 sine theta? Have you noticed that the only difference is I'm calling theta t? Does that make sense? Now, if I want the whole circle, then won't the start value of t and the finish value of t be 0 and 2 pi? If I wanted the top half of the circle, because sometimes you do, right? Because maybe your curve is just this piece, right? Then wouldn't the answer be 0 to a half pi? No, 0 to pi, I should say. If I wanted a quarter circle, wouldn't it be 0 to half pi? So would you agree that this is much more versatile? That you can do a whole circle, the top half, the bottom half, the first quadrant bit, by just adjusting these fellas. Agreed? Now, every single circle is basically going to be the radius cosine t and the radius sine t. Are we good? Now, still skill building. To be able to do a line integral, one of the things we're going to have to do is we're going to have to convert the dx and the dy into dt's. It's pretty close to, very equivalent to substitution. Right, so let's give you a parametric equation. Suppose I had a curve that was t cubed plus t, and the y coordinate was the sine of t. Right. That would probably look like on the floor some kind of curve that would go up and down like a yo-yo, like a sinusoidal curve, right? Would look kind of like that side there, flattened on. Now, let's take the first one. Think of that like a u-sub. If I differentiate this guy with respect to t, don't you get 3t squared plus 1? And won't dx then be 3t squared plus 1 dt? I have now converted dx into t's. Now, y was sine of t. So differentiate y with respect to t, you get cosine t, and do the little crossover thing. Have we got that guy? You want to see another one of those, or does that process seem okay? How to take a parametric equation, x and y in this case, and convert it into t's. Looking good? Okay, I'm moving on. Notation now. Imagine we had this parametric equation. It's very often convenient to write it as a space curve. Now, can you remember space curves in Calc 3? Right. So notation-wise, this is just a little bit less work. Right. Now, for instance, won't r dashed of t be 2t plus 2 e to the t, right? We go with that? Yeah. There's a guy that you're going to meet in these questions called ds. ds is r dashed of t dt. It's basically taking those guys and writing them down in a convenient, concise format. Are you comfortable about r of t, what it looks like when you convert a parametric into a space curve, and what the derivative would look like, and that ds is replaced by this? We've now got all the pieces that we need that we're now going to put together to get a line a line integral. So let's suppose I want to find the line integral over a curve C, and it's going to be called xy squared ds. So that's what it will look like originally before it gets changed. And they are going to tell you the parametric equation of the curve. And let's say that the parametric equation of the curve is t squared plus t, and that y is, I don't know, e to the t, and that t is going to go from 0 to 2. So in this question, you didn't need to create the parametric equation. Do you see they're giving it to you? But in some questions, they're going to say the curve is the line joining 1, 2 to 7, 9, right? In which case you need to create it. Or the curve is y equals 4x squared. All right, you'd have to parametricize that, right? But in this case, you got that bit free. So what does it look like as a new integral? Well, it's going to be converted. Everybody is going to be converted into t's. So it's going to be from t equals 0 to equals 2. The x is going to be replaced by t squared plus t. The y squared is going to be replaced by e to the t squared. And the ds is going to get replaced by r dash t dt. So far, so good. So it's going to be the integral from 0 to 2 of t squared plus t e to the 2t times, well, if you do a derivative of this guy, isn't it 2t plus 1? Missing something here. What am I missing? Oh, yeah. Forget what I just did. I combined two techniques together, which was not a cool idea. So let me unconnect this fella and tell you the formula that we are going to use. The one that I was trying to use does exist. It's going to be that guy. So I'll use the same question. So it's going to be, where are you? It's going to be x squared y, the square root of this guy squared plus this guy squared dt. The x is going to be replaced by t squared plus t. The y is going to be replaced by that guy. The derivative of this guy is 2t plus 2 squared. The derivative of this guy is e to the t squared. And so I'm now looking at and I am going to put a dot, dot, dot in that, not because it's doable, but if you could integrate that, wouldn't that be the answer? I should never make up my own questions because they never come out pretty. And I still don't learn that lesson. And I didn't, for instance, pay attention to that particular version of the line integral because I was too busy thinking of the next section where we do that guy in a totally different way, right? So.
You want to say hello in chat now?
Good idea. Why don't you say hello? And I will look for a real question from the textbook so I won't get caught up on issues. Okay, hopefully in the next few minutes or seconds. Here we go. We good? Everybody said hi? Let me go in then. Here is the kind of line integral that I was talking about earlier with all the dx and dt stuff. And that's the one I should have done before I ended up picking version number 2. So this is version number 1. This is what the line integral looks like. In this case, we're looking for a line that joins this point to that point. So step 1, find the parametric equation. In this case, it's a line, so let's go through the process. If I call this one x1, y1, and I call this guy x2, y2, would you agree that the direction vector is 7 take away 0, 1 take away 0? It's pretty easy to do. And the x then will be 0 plus 7t, and y is 0 plus 1t. So here's our parametric equations. Now, if x is equal to 7t, won't dx by dt be 7? And won't that make dx 7 dt? And if y is t, then dy by dt is 1, and that makes dy 1 dt, so it's just a dt. So what we're going to do is we're going to take every single piece of this and convert them into t's. So that's what step 2's do. So I've got an integral of x, which is 7t, plus 7y, which is 7t, a dx. Well, a dx in this case is 7 dt, plus an x squared, which in this case is 7t squared, times a dy, which is just dt. So far, so good. Now, I need to know where to start, what t value to begin, and what t value to end. And I've actually told you at the start. If it's a line joining here to here, won't t equals 0 give you the start? What value of t will give you the second point?
1.
1. Are we comfortable about where that 0 and 1 for t came from? Do you notice that this isn't your normal integral? It's kind of weird looking because isn't there a dt and then another dt? What you're allowed to do then is you're allowed to take 7 times that, that's 49t, 7 times that, I wish I'd added them together, but too late now, and this guy, and have them over 1 dt. Does that make sense? You could just combine them into a single dt. And so it's going to be the integral from 0 to 1 of 98t plus 49t squared dt. Is that good? Right. So let's not do the square root dx dt squared plus dy by dt squared. Let's worry about them tomorrow, right? Let's just focus on the line integrals that are the form something dx, something dy, right? So I'm going to focus on this. So another version of that question could look like this fella. The line integral of c of x dx plus y squared dy plus z cubed dz, and the curve C has parametric equation t squared, 2t, 3t cubed, and you're told that t goes from 0 to 1. Right? So this is a 3D guy. You can see it's made up of a dx, a dy, and a dz. Let's see if we can speed this process up. 0 to 1 because of that. X, well, that's t squared. What's dx?
2t dt.
Now, there's different approaches to this question. Let me show you a different approach. Couldn't I just split them into 3 separate integrals and then just do them that way? So y squared becomes 2t squared, and won't dy be 2 dt? And z goes from 0 to 1, and z cubed is 3t cubed, and the derivative of that guy, darn it, is going to be tight, 9t squared dt. So the first one is the integral of 2t cubed dt. The second integral is 4t squared, 8t squared dt. And the last integral is 3, that's 9. 2 more, that makes it 11. 3, 9, 20, 81, 243, I believe, dt. Can I just dot that now? Now, one of the unusual things about line integrals is that you don't actually always have all 3 components. So for instance, you could just get this guy. The line integral of x squared y, but only focusing on what z would look like.
Yeah, someone in chat said it's 151 or 1051. I mean,
It is?
Yeah.
My watch is really out. I think it's 46. Is it 1051?
yeah, that's what my computer says.
Okay, my watch is out. Sorry for keeping you guys. We will continue tomorrow, where we'll look at some more dx, dys, dz's, and I will also show you how to do that r-t dt thing that I kind of skipped. Okay, bye-bye. I'll see you, Dom. See you all
Have a
tomorrow.
good one.
Bye. Good grief, my watch is really out. Hi, James. You haven't seen any phantom versions of me lately?